Now we come to G3, work. And we're going to do this by thinking of a problem of folks pushing things across a room. Say we have a flat horizontal surface, and we have folks pushing refrigerators, say dishwashers, and they're going here where it's going to be some kind of a big truck that we're going to load up here and then cart the stuff away. Oh, there you go. Here's one of our possible employees. All right. Courtesy Mingo from Flickr. And the problem that we're dealing with here doesn't matter if you're pushing with heavy wheels or not. So the idea is if we're going to pay people based on the actual work that they do, what we would consider is that the work, and here W stands for work, is proportional to the distance. That if you push farther, you should get paid more. Some of the things are really far away from the loading dock here in this warehouse. So if you're taking things from way back here, you should get rewarded. And also, you should get rewarded for the force, because if you're pushing a refrigerator, that's going to be more force you need compared to something that's smaller. So this suggests that we look at a definition where we have a block, and we have a force, say F, and we have a distance, D. Suggests we do force times distance. And that is the definition we use in physics. It's a new physical quantity. And what would be the units? Well, the force in the metric system is newtons, and the distance here would be meters. And the Newton times meter, is named after joule. So this is joule. Joule, that would be a scientist that showed that energy, work, this kind of thing, work is related to energy, heating, some water or heat energy. And we'll talk about heat later in our course. So the joule is equal to the Newton. Remember, we don't capitalize when we're writing out the units, Newton meter. Now, if we want to study this a little bit more, this dimensional analysis, the Newton is equal to force equals MA. So that's M kilogram, acceleration is meters per second squared. So I can substitute for the Newton this expression, and this will give me kilogram times meters squared over second squared. It's interesting here how the big three, if we look at the big three, for example, we have, say, a length, we have the time, and say we have here mass. Okay, so this would be like your kilograms. Then what you could do is when you analyze this situation, you could say, well, here's a formal way of writing it. The work is the dimensions of the force times the distance. And this would, for force, you have MA, so you would do this. And then here you could write down for the dimensions of the mass, we could just, in a sense, keep it generic with these three capital letters. Say that's M, acceleration is length over time squared, meters per second squared, and then the distance would be length. So then you could write this down as a mass, length squared over the time squared, or mass L squared T to the minus 2. So that's kind of neat that you could write the dimensions in that way. I had said earlier that in this course we can get pretty much all of our physical quantities, the ones that we derive from the big three: your length, your time, and your mass. Well, what about the other units? Well, the other units, if you look at the, say, CGS system, the metric system, where you have the force in dynes, and you have centimeters for the distance, that's called erg. I see that, by the way, in crossword puzzles a lot. And then in the British system, say if we're looking at the British system, you would have here pounds, times feet. But so they just call that pounds, feet, or if you like foot pounds. That kind of sounds maybe better that way in English, so they say foot pounds. So let's look at two cool cases of no work. And if we pay folks not by the hour, but by the work they do, then we'll give no money to case one, the zombie. Now the zombie goes around walking, so the zombie will go a distance d, but the force is equal to 0, just push in air. So in the definition of force times distance, you're going to get 0, no work. Now, the second one we'll call up against the wall. So someone decides there's, say, a wall, pushing against a wall here, say some kind of wall like that. So the person is exerting a force, but the distance is equal to 0, not moving anything, right? So anyway, you would get no work done, because d is 0. Now what happens if we have the mass and we're applying the force at an angle like this, theta, and then we're going to move a distance d? Well, the definition of work now is force d times cosine of theta. In other words, you take the component of force here, you take the force times the cosine of theta, that's the force in the direction of motion, and use that. So this is the formal definition. And our ideal model breaks down, because if someone wanted to push up a little bit to ease up on the friction, that would be smart, but according to this definition, you would be applying less force and you'd get penalized, so breaks down. But anyway, we have our definition. This was just to help us get our definition. You see, it makes kind of sense to set up things this way. So now this brings us to a formal mathematical manipulation called the dot product, where you take two vectors, because force is a vector and displacement is a vector. See, this is vector d to go from, let's say, starting point to the end point, and force is a vector. So what you do is you take the force vector dot d, this is the definition called the dot product. It's a definition. And you take two vectors and you wind up with a scalar, something that has no direction. So the dot product. Some introductory physics courses will spend the first week in class, teaching about things like this to be used later. I prefer to wait until we actually need it and then introduce it.